On Independence Day, more than 150 million hot dogs are consumed across the United States, enough to form a continuous line stretching from Washington, D.C. all the way to the Pacific coast. But have you ever wondered? They're both sausages. So what makes a hot dog something entirely different? The journey begins across America's vast grasslands, the starting point of a livestock system with nearly 90 million head of cattle. From there, the meat moves straight into modern processing lines, where it's emulsified into an ultra-fine structure, creating hot dogs with nearly identical texture, flavor, and shape. Today, join Agriculture Insight as we go inside the system behind one of America's most iconic foods. From cattle breeds you may have never heard of, to the secret behind that signature snap in the middle of a roaring baseball game. How many hot dogs could you eat in a week? At the Nathan's Famous Hot Dog Eating Contest, run by Nathan's Famous, a brand that grew from a small pushcart in Coney Island in 1916 into a benchmark for the American-style hot dog, top competitors can consume up to 76 hot dogs in just 10 minutes. In essence, a hot dog is a type of sausage, but what sets it apart is its finely emulsified structure. While many sausages retain a coarse grind or visible meat texture, hot dogs are fully processed into a uniform emulsion, forming a smooth, elastic consistency and delivering that distinctive snap when you bite through the collagen casing. Few people realize that the hot dog bun was born out of the inconvenience of traditional sausages. In the 19th century, street vendors would lend gloves to customers so they could hold hot sausages, but many ended up taking the gloves home by mistake. Placing the hot dog inside a long bun was not just a cost-saving solution. It became a design breakthrough. It allowed people to hold and eat it with one hand, without heat or mess. Now let's explore heritage cattle breeds to understand why beef, despite its popularity, often takes a backseat to pork in industrial hot dog production. In the Scottish Highlands, around 25,000 registered purebred Highland cattle are maintained to preserve their genetics and uphold premium meat quality. Highland cattle are instantly recognizable by their long horns and thick coats that often cover their eyes. This coat actually consists of two distinct layers: a long, coarse outer layer that protects against rain and wind, and a soft inner layer that provides insulation. Thanks to this natural adaptation, they can withstand harsh cold climates without needing to build up thick subcutaneous fat. As a result, Highland beef tends to be leaner, more tender, and richer in flavor compared to grain-fed beef. However, this is exactly where the economic challenge lies for modern livestock production. Highland cattle take 24 to 30 months to reach slaughter weight, nearly twice as long as industrial breeds. Their slow growth, lower yields, and higher grazing and management costs push prices to around $15 to over $75 per kilogram, significantly higher than conventional beef. Leaving the windswept highlands behind, we move to another distinctive breed, belted Galloway cattle, often nicknamed Oreo cows in the US, thanks to the striking white band across their black bodies. Like Highland cattle, belted Galloways also have a thick double coat, allowing them to thrive on year-round grazing without the need for grain finishing. In temperate grazing regions, such as the northern United States, herds are often rotated across multiple pastures. This rotational grazing system allows grass to recover, reduces waste buildup, and keeps the environment cleaner, helping calves grow stronger while lowering disease risk. Although they grow only about 2 to 4 months faster than Highland cattle, belted Galloways produce high-quality beef with excellent tenderness and balanced marbling. Notably, their dressing percentage can reach around 55 to 60% of body weight, a relatively high figure for fully grass-fed cattle. So if you were running a ranch, would you invest in heritage breeds to target the premium meat market, or prioritize fast-growing industrial cattle to maximize efficiency and output? In modern processing plants, meat from farms is transported in and fed into fully integrated production lines, where hundreds of thousands of hot dogs can be produced every hour before making their way to supermarkets, stadiums, and fast food stands across the United States. Around 60 to 80% of hot dogs on the market are made primarily from pork, the top choice in industrial processing due to its superior emulsification properties. Pork fat is soft and disperses easily, helping create a juicy texture, stable smoothness, and significantly lower costs compared to beef. After undergoing humane slaughter, pork carcasses are split lengthwise using automated saw systems. The meat is then broken down into primary cuts such as shoulder, ham, and belly. Among these, pork shoulder is the most preferred thanks to its balanced lean-to-fat ratio and high levels of myosin protein, a key factor that binds fat, water, and meat together during processing. Immediately after breakdown, the meat is transported to the plant and sent straight to the trimming area, where workers use specialized knives to remove tendons and tough connective tissue, keeping only the clean, soft muscle. This step ensures the final emulsion remains smooth, free of air pockets, and structurally stable during heating. Once all tough connective tissue has been completely removed, the meat enters its first structural transformation inside high-capacity grinders. A rotating screw continuously pulls and compresses the material forward, forcing it through metal plates with extremely fine holes. Within seconds, both muscle and fat tissues are broken down, turning loose chunks of meat into soft, uniform strands of consistent size. However, this step is only the beginning. To achieve the ultra-smooth, almost creamy texture that defines hot dogs and sets them apart from traditional sausages, the mixture is transferred into massive emulsifying cutters, where blades can spin at up to 3,000 revolutions per minute. At this point, crushed ice is added directly into the machine to keep the mixture within an ideal range of 10 to 12 degrees Celsius. This step is critical because even a slight increase in temperature can denature the proteins prematurely, destroying their ability to bind and causing fat to separate, turning entire batches of raw material into a loose, unusable mass. While the machine continues running at high speed, seasonings are added to define the product's signature flavor, including salt, pepper, garlic, sugar, as well as spices like chili powder or mustard powder. To enhance juiciness and create the characteristic elasticity, stabilizers such as phosphates are introduced. At the molecular level, these act like a binding agent, helping proteins retain water and effectively link fat with lean meat, preventing separation during heating. The distinct color variations seen in the market are also determined at this stage. For the classic reddish-orange American-style hot dog, manufacturers often add paprika extract, chili powder, or small amounts of nitrite salts. When exposed to heat during cooking or smoking, these compounds react with meat proteins to produce a stable, appealing pink-red color that does not fade over time. In contrast, products with fewer additives or no nitrites retain a more natural meat color, relying primarily on seasoning for flavor. From here, the mixture is blended more thoroughly to form a stable emulsion. At this level, fat, water, and protein are no longer separate components, but are tightly bound into a uniform, smooth, and elastic mass, essentially a meat paste that forms the foundation of the hot dog's signature texture. Once the emulsion reaches the target smoothness, the line moves on to stuffing the meat into casings. This step is now almost fully automated. The stuffer maintains a steady pumping pressure while removing as much trapped air as possible, because even a tiny air pocket can create visible pitting on the hot dog's surface after cooking, ruining that clean, smooth look. Ever wondered where that signature snap comes from when you bite into a hot dog? It comes far less from the meat than from the casing itself. Typically natural casings, most commonly pork or sheep intestines. Before loading, the casings are thoroughly rinsed and soaked in warm water to restore their natural elasticity, making them easier to mount on the stuffing horn and flexible enough to stretch without tearing. At the head of the machine, an operator pulls the casing over the nozzle and gently holds the leading end to control the outflow. As the machine runs, an internal auger pushes the meat forward in a steady stream, filling the casing from the inside out while minimizing air pockets so the hot dogs don't blister or burst during cooking. Even though the machine does most of the heavy lifting, human control is still critical at this stage. The operator needs a precise touch to guide the casing and feel the tension as it fills. Too loose, and the sausage will look misshapen and lack firmness. Too tight, and the pressure can build up and cause the casing to split as soon as it's heated. That's why, when you put a hot dog on the pan, some turn glossy and taut with a slight, satisfying split, while others simply soften. The difference was already decided the moment it passed through the stuffing horn. Right after this step, hot dogs enter the hottest stage of the process, where they are fully cooked. The sausages are hung on stainless steel racks and moved into thermal chambers for heat processing. Depending on the product type, manufacturers typically choose between two specialized methods: steaming or smoking. But before entering the chamber, they are often sprayed with water to keep the surface hydrated, preventing the casing from drying out or cracking when exposed to sudden high heat. With steaming, the sausages are placed in industrial steam ovens, where the temperature is carefully maintained between 167 to 185 degrees for about 30 to 60 minutes. This allows them to cook evenly from the inside out while preserving their natural moisture. For smoked varieties, the sausages are transferred into sealed chambers and exposed to smoke generated from wood or sawdust. This gives them their signature glossy brownish-orange color and a rich, smoky flavor. Beyond simply cooking the meat, this stage also stabilizes the protein structure, helping the hot dogs achieve their characteristic firmness and that clean, elastic snap. After leaving the heat chamber, the sausages still retain a significant amount of residual heat, so they must be cooled almost immediately to bring the temperature down quickly. Otherwise, this leftover heat will continue to cook the meat, causing the structure to become soft and compromising its juiciness. This rapid temperature drop, often referred to as a thermal shock, is a critical step that helps lock in flavor while allowing the casing to contract slightly, preventing wrinkles during packaging. Finally, all qualified hot dogs move on to sealed packaging, using either vacuum sealing or modified atmosphere packaging. This helps retain moisture, limit oxidation, and extend shelf life for several weeks. In the United States, the finished products are then transported through a cold chain to distribution centers and quickly delivered to supermarkets and convenience stores, kept at consistently low temperatures all the way until they reach the consumer. Each year, Iceland experiences frequent small eruptions due to its position on the boundary between two tectonic plates, where lava can exceed 1,000 degrees Celsius, hot enough to cook food using the heat retained within the rock itself. While the rock isn't inherently toxic, surrounding sulfur gases and mineral dust mean cooking directly on it is only safe when properly controlled or when the food is protected. It sounds crazy, but in Iceland, scientists have actually placed hot dogs directly onto lava that has cooled on the outside but still retains intense heat within, turning it into a natural grill in the middle of the landscape. And surprisingly, this very country, a North Atlantic island of just over 300,000 people, sitting on a volcanic belt filled with ancient lava fields, consumes more hot dogs per capita than anywhere else in the world. While in the United States, hot dogs are tied to stadiums and large events, in Iceland, they're simply an everyday comfort food. A quick, warming meal with no special occasion required. Whether at an American stadium or in the volcanic landscapes of Iceland, hot dogs show up as a quick, convenient choice, something you can grab without a second thought. However, a typical hot dog contains around 700 to 900 milligrams of sodium, nearly 1/3 of the recommended daily limit. Something that matters even more given how high the average American diet already is in salt. When combined with other processed meats, total sodium intake can easily exceed safe levels without you realizing it. In addition, preservatives such as nitrates and nitrites, when exposed to high heat, can form compounds called nitrosamines, substances that have been linked to increased cancer risk with long-term consumption. So if you want to avoid quietly building up risks to your heart and blood pressure, what matters most is how often and how much you eat. because the same convenience and familiarity that made hot dogs a cultural icon can also make them easy to overconsume if you're not paying attention. And now, let's head to California, where vast fields stretch beneath year-round sunlight, where warm temperatures and fertile soil quietly nurture cayenne peppers, the very ingredient behind the signature heat of famous sauces like Frank's. The process begins in shaded nurseries with trays carefully filled and seeds placed into individual cells, covered with fine soil and kept consistently moist. After about 7 days, the first shoots emerge, but this is only the beginning. Farmers continue to monitor each tray, adjusting light and water and removing weaker seedlings early to ensure uniform growth. In the past, everything was done by hand. Farmers bent over row after row, digging small holes, placing each seedling carefully, covering it with soil and watering it. A full day of work could only cover a small area. It was slow, but precise. Today, many farms in California rely on specialized transplanting machines. These machines move steadily along the rows, automatically creating holes, placing seedlings, and covering them within seconds. A single machine can replace up to 50 manual workers, ensuring each plant is set at the right depth and spacing with remarkable consistency. Yet, whether by hand or by machine, the most important part remains unchanged: daily observation. The plants respond quickly to changes in soil moisture or weather. If not corrected in time, yields can drop by up to 30%. But when everything is managed well, each plant can produce nearly 2 kilograms of peppers, and the entire field gradually turns a vivid red, the clearest sign of a truly successful harvest. After about 5 months from planting, cayenne pepper plants in New Mexico begin their harvest season, typically from August to October, when entire fields turn a vivid shade of red. Harvesting is never random. Workers rely on color, skin firmness, and stem strength to determine whether each pepper meets the standard. Only those with a uniform red color, smooth skin, and no damage are selected, because even a single poor quality pepper can affect an entire batch of sauce. An interesting detail is that peppers don't ripen all at once, so each field must be harvested multiple times, spaced a few days apart. What seems like a simple task is actually far from easy. It requires both experience and a great deal of patience. Workers spend hours bent over under the sun, carefully selecting each pepper one by one, and before long the strain begins to build in their backs. In vast chili fields spanning hundreds of hectares, harvesting is no longer done by human labor alone. It is powered by massive, specialized machines. These harvesters move along the rows, using shaking and cutting mechanisms to separate ripe peppers from the plants, then carry them onto conveyor belts for on-site sorting. In just 1 hour, a single machine can pass through tens of thousands of plants and process up to 10 to 15 tons of peppers, a speed that would take an entire crew working for days to match. However, this efficiency comes at a cost: precision. Machines cannot perfectly distinguish which peppers meet the highest quality standards, so mechanically harvested peppers must go through additional sorting systems afterward. For premium hot sauce production, the human touch still remains irreplaceable. After harvest, in many traditional production regions, chili peppers are not sent to factories right away, but are spread out under direct sunlight, beginning a slow yet decisive transformation. Billions of vibrant red peppers are laid across drying yards or large mesh racks, left to sun-dry for 3 to 7 days under temperatures that can exceed 35 degrees Celsius. But this is more than just drying. As moisture evaporates, the structure of the peppers changes. Compounds like capsaicin become more concentrated, while natural sugars are compressed, creating a deeper, richer heat with a lingering finish that fresh peppers simply cannot achieve. However, this process is also a gamble with nature. A sudden rain or a spike in humidity can ruin an entire batch. That's why, despite its unique flavor, this method is now mostly reserved for small-scale artisanal production. used by brands like Yellowbird Sauce and Queen Majesty Hot Sauce to craft sauces with truly distinctive character. In modern factories, chili peppers don't wait. Within 24 hours of harvest, they are sent straight into processing lines to preserve their freshness and natural flavor. Here, the peppers are washed in industrial systems using high-pressure water and rotating drums to completely remove dirt and debris. They then move along conveyor belts through sorting systems, where unripe, damaged, or substandard peppers are removed, ensuring that only the best quality peppers proceed to the next stages. This approach creates a completely different flavor profile compared to sun-dried chilies. Fresh peppers retain their moisture, delivering a bright, sharp heat that spreads quickly, while dried peppers, having lost up to 70 to 80% of their water content, produce a deeper, richer heat that lingers much longer. In modern factories, instead of being sun-dried, chili peppers are typically processed in industrial drying systems to ensure strict quality control. After being washed, the fresh peppers are transferred into drying chambers, where temperature and airflow are precisely regulated, usually maintained at around 50 to 70 degrees Celsius for several hours. After being cleaned, the peppers are fed into high-capacity grinding machines, typically hammer mills operating at speeds of up to 3,000 revolutions per minute. Within seconds, the cellular structure of the peppers is completely broken down, releasing capsaicin, natural red pigments, and aromatic compounds, forming a uniform slurry known as pepper mash, a thick mixture of pulp, juice, and seeds. The mash is then blended with salt at a ratio of about 3% and transferred into large fermentation tanks, where it undergoes a fermentation process lasting around 8 weeks, typically maintained at approximately 32 degrees Celsius, 90 degrees Fahrenheit. In this environment, lactic acid bacteria, such as lactobacillus, convert the natural sugars in the peppers into lactic acid, creating a mild tang while naturally stabilizing and preserving the mixture. Throughout this process, the mash continuously releases carbon dioxide, CO2, and evolves day by day, almost like a living system in motion. What's remarkable is that the heat doesn't diminish, it simply changes in perception. Capsaicin remains intact, but as it interacts with acids and newly formed aromatic compounds, the heat becomes smoother, deeper, and more evenly distributed, rather than sharp and aggressive like fresh peppers. For sauces like Tabasco, fermentation doesn't take place in modern steel tanks, but in specially selected oak barrels that were previously used to age whiskey. After being ground and mixed with salt, the pepper mash is transferred into these large wooden barrels, sealed and topped with a layer of salt to prevent air from entering. Under these nearly airtight conditions, the mash is aged for up to 3 years, an exceptionally long period in the food industry. The barrels naturally breathe, allowing a tiny amount of oxygen to enter, just enough to sustain fermentation without spoiling the mixture. During this time, the mash doesn't just ferment, it matures, much like wine. The flavor becomes deeper, rounder, and less harsh with each passing year. As a result, Tabasco isn't just hot sauce, it's one of the few sauces that is truly aged like wine, where time itself is the most important ingredient, shaping its flavor. After the fermentation process is complete, the pepper mash is pumped into large industrial mixing tanks, each capable of holding up to 50,000 liters. Here, the mash is combined with vinegar and a carefully controlled blend of spices, following a precise, standardized formula. The mixture is then gently heated for about 3 minutes at a controlled temperature, just enough to stabilize microbial activity and activate its aroma, without actually cooking or damaging the natural flavor structure of the peppers. It is then transferred into continuous mixing tanks for around 4 weeks, where the vinegar gradually penetrates every part of the mash, breaking down its original structure and transforming it from a thick mass into a smooth, uniform liquid sauce. This stage is critical in creating the balance between heat, acidity, and aroma. If done too quickly, the sauce may separate. If left too long, the flavor can become flat and muted. Once the mixture reaches a stable state, it is passed through a multi-stage filtration system using ultra-fine meshes of around 0.5 to 1 millimeters, where all seeds and fibrous material are completely removed. This step defines the signature texture of industrial hot sauce: smooth, viscous, and perfectly uniform, with no graininess and no separation. The entire final processing stage, from mixing and heating to filtration, takes place in under 1 hour. Yet it determines nearly the entire sensory experience of the product. From a raw, fermented mash, the system transforms it into a finished hot sauce, ready for bottling at speeds of up to 500 bottles per minute, a scale that would take weeks to achieve if done manually. After filtration is complete, the smooth and uniform hot sauce is pumped directly into an automated bottling line, one of the fastest and most precise stages in the entire factory. Pre-cleaned and sterilized glass bottles move continuously along conveyor belts, passing under filling nozzles calibrated to dispense exact volumes down to the milliliter. In a split second, each bottle is filled with remarkable precision, with only minimal deviation. Immediately after filling, the bottles move to an automated capping system, where plastic caps are tightened with consistent torque to ensure an airtight seal. A protective seal is then applied to preserve quality during transportation and storage. The process continues with labeling and final inspection, where each bottle is scanned to detect any issues in fill level, sealing, or appearance. Operating at speeds of up to 500 bottles per minute, this stage doesn't just complete the process, it transforms months of production into a finished product ready for the table in a matter of seconds. The journey of making a burger begins inside massive industrial mixers, where flour, yeast, water, sugar, salt, butter, and eggs are adjusted according to McDonald's proprietary formula, a system of ratios that exists only within internal production specification sheets. Inside the factory, the dough is never kneaded by hand. It is pressed, stretched, and twisted by machines capable of handling 1–2 tons per batch, spinning at over 100 revolutions per minute. After mixing, the dough is transferred to a controlled proofing stage, where the temperature is maintained at around 30 degrees Celsius and humidity is kept stable to allow the yeast to perform at its optimum. Next, the dough is automatically divided into precise portions, typically ranging from 60 to 70 grams, a figure carefully calculated so that, once baked, each bun reaches a diameter of about 10 centimeters, fitting perfectly with a standard hamburger patty. Before entering the oven, the surface of the buns is misted with steam and coated with a thin layer of egg wash, creating the signature golden color. In less than 12 minutes of baking at temperatures above 200 degrees Celsius, thousands of identical buns are completed, uniform, precise, and ready for the next stage of the production line. Once cooled, the buns are cleanly split in half by an automated slicing machine, ready for the packaging stage. The bun halves are then placed onto conveyor belts, neatly aligned and sealed using airtight packaging systems, helping preserve freshness and optimal flavor. In a hamburger, cheese is not just added for richness, it is engineered to melt at precisely the right moment. Most major burger chains use processed cheese, often based on cheddar or American cheese, enhanced with emulsifying salts to control its structure when exposed to heat. As a result, the cheese begins to soften at around 60 degrees Celsius and fully melts at approximately 75 to 80 degrees Celsius, evenly coating the patty without separating into oil or clumping. A change of just a few percentage points in moisture or fat content can cause the cheese to melt too quickly or unevenly, disrupting the familiar smooth, creamy sensation of a perfectly made hamburger. Once the buns are completed, the production line immediately shifts to preparing the meat patties. On a parallel processing line, the patties are handled within a closed system, beginning with the selection and cutting of beef into standardized sizes, before being fed into high-capacity grinders to create a smooth, uniform mixture. What few people realize is that each patty does not come from a single cow. Rather, it is the result of a carefully controlled blend from around 200 cattle per day, designed to lock in flavor and ensure that every burger leaving the factory delivers the same familiar taste. Once the meat mixture reaches a smooth, cohesive texture, it is fed into patty-forming machines, systems programmed with near-absolute precision. Here, the meat is pressed into perfectly round patties, with thickness and structure tightly controlled. Pre-calculated pneumatic pressure ensures each patty is firm to the touch without cracking or breaking. Immediately after shaping, the patties are sent through a rapid chilling stage where powerful streams of cold air reduce the temperature to around 0 degrees Celsius in just 3 to 7 minutes. This process locks in the meat's structure, preserving moisture and ensuring an ideal tender texture when the patty is later cooked. When all the ingredients are ready, a McDonald's burger begins to be assembled through a process that has been standardized to near perfection. The bun is placed onto a hot grill for just a few seconds, enough for the surface to lightly toast and release its signature buttery aroma, while the inside remains soft and familiar. A layer of McDonald's signature sauce is applied with precision using a calibrated dispenser, just enough to bind the components without soaking the bread. Next, the layers are stacked in a pre-programmed order. Finely shredded lettuce for a fresh crunch, evenly sliced pickles for that familiar tang, a perfectly cooked beef patty, and on top, a slice of cheddar cheese that melts at exactly the right moment. Not too early, not too late. The entire process takes only 30 to 40 seconds, yet the result is a burger with a consistent flavor profile, whether you take a bite in New York, Tokyo, or Paris. That is how McDonald's turns a simple burger into a global product. We leave behind the McDonald's factory, where hamburgers are replicated every second. Next, we turn to another empire, the world's most globally widespread fried chicken chain, operating a machine worth tens of billions of dollars each year, KFC. The journey of KFC chicken begins at dawn, when refrigerated trucks carrying fresh poultry leave the farms and head straight to the processing plant, where every step is timed down to the second. Upon arrival, the chickens are pre-cleaned and immediately fed into an automated production line with almost no downtime. Within minutes, they reach the leg separation area, where industrial cutting blades, calibrated to match the natural structure of the joints, operate continuously at a capacity of around 10,000 units per hour, ensuring uniform sizing. The carcasses are then transferred to the evisceration stage, where vacuum-based systems remove the internal organs in just 3 seconds. The pressure is precisely controlled, strong enough to clean thoroughly, yet gentle enough to preserve the integrity of the meat, marking a critical step in maintaining hygiene, quality, and consistency before the chicken moves on to the next stages of processing. Immediately after the initial cleaning and sorting stage, the chickens are transferred to a dedicated wing cutting line. Here, each bird is placed into a mechanical positioning mold that holds it in the correct orientation before automated blades make precise cuts at the wing joints. This entire section is designed to operate continuously in production shifts lasting up to 18 hours per day, ensuring a stable supply for thousands of restaurants across the same region. Once separated, the wings are moved onto a separate conveyor for inspection and classification. The remaining carcass then enters the central processing line. Throughout this sequence, from halving the body to separating the breast and sorting the thighs, the ambient temperature is maintained below 10 degrees Celsius to slow microbial activity and preserve the meat's structure. The body is split along a fixed axis, the breast is removed using controlled pulling force, and the thighs are routed to a separate line, all to ensure that each piece of chicken behaves almost identically when it later enters KFC's pressure fryers. From this point on, the chicken enters the most critical stage, where KFC's legendary recipe is finally activated. On an automated conveyor, the chicken moves continuously through the dry coating station, a secret blend of 11 herbs and spices, including salt, black pepper, paprika, garlic powder, onion powder, mustard powder, celery powder, dried ginger, oregano, thyme, and white pepper. The key does not lie in the ingredient list alone, but in the blending ratios and the order in which the chicken comes into contact with them. As the first dry coating is applied, the spices adhere directly to the surface of the meat. The wet coating that follows dissolves part of the essential oils, awakening the aroma. Finally, a finishing layer of dry coating locks the entire structure in place, laying the foundation for the crispy, aromatic, and richly flavored crust that defines KFC's pressure-fried chicken. Once the chicken pieces have been pre-processed and coated at the factory, they are transported under refrigeration to individual KFC restaurants and enter the final cooking stage. In the kitchen, the chicken is kept at low temperatures until frying time, then placed directly into pressure fryers, the key equipment that defines KFC's cooking method. The frying oil is heated and maintained at around 170 to 175 degrees Celsius. Thanks to this high-pressure environment, the chicken cooks faster without drying out. The outer coating becomes distinctly crispy, while the meat inside remains tender and juicy. Frying times are strictly controlled for each product type, after which the chicken is removed, drained of excess oil, and transferred to warming trays. The entire in-store process is designed so that every batch of chicken served has the same color, texture, and flavor, regardless of who prepares it or what time of day it is cooked. Alongside its traditional bone-in fried chicken, KFC has developed small chicken pieces by cutting boneless chicken into bite-sized portions, rather than grinding or molding the meat like industrial nuggets. Each piece remains whole muscle chicken, simply divided into smaller cuts to suit faster eating habits and shareable meals. Thanks to their smaller size, these pieces cook faster and more evenly in pressure fryers. With temperature and pressure tightly controlled, frying time is reduced by around 20 to 30% compared to larger cuts, while the meat inside stays tender, juicy, and well hydrated. At the same time, the coating fully covers the surface, creating a deeply crispy, evenly golden crust that delivers KFC's signature flavor. Cheaper than Pizza Hut, faster than Papa John's, and generating revenue far beyond the rest of the pizza world. That is, Domino's, a pizza machine powered by speed, technology, and scale, with annual revenue of USD 40 billion. The journey of producing nearly 3 million pizzas each day at Domino's Pizza begins with massive ingredient tanks inside highly automated production centers. Like everything in the fast food industry, pizza dough has its own formula. Flour, water, oil, salt, and sugar are measured precisely down to the gram, combined with Domino's Pizza's proprietary recipe that only a very small group of senior executives can access. The mixture is then fed into large industrial mixers, where powerful paddles continuously press and stretch the dough in a fixed cycle. This mixing force develops a smooth, elastic, and uniform dough, while temperature is tightly controlled to ensure that every batch delivers exactly the same result. After mixing, the dough is portioned and rounded entirely automatically. Each dough piece is cut to a pre-programmed weight, approximately 150 grams for small pizzas, 250 grams for medium, and 380 to 400 grams for large. The dough then passes through rollers and shaping surfaces that stretch the outer skin, forming smooth, round, airtight dough balls. The entire process takes less than 10 seconds per dough ball, moving too fast for human intervention. This stretched surface structure helps the dough maintain its shape, rise evenly, and resist tearing when stretched into a pizza base. On each production line, the system can operate continuously for hours, producing enough dough to supply hundreds of stores within the same region. The dough balls for small, medium, and large pizzas are then placed precisely into molded trays, ready for cold fermentation and distribution. Next, the dough enters a massive spiral cooling system, where the temperature is reduced to 3 to 4 degrees Celsius to slow down fermentation without compromising the quality of the dough. Domino's does not operate frozen pizza factories. Every pizza is made fresh at each individual store and sent straight to the customer. In Domino's kitchens, the dough is taken out to naturally return to temperature before being placed on a cornmeal-dusted work surface. The motions of rotating, pressing, and supporting the dough with the back of the hand are not just about shaping, it's about pushing air from the center toward the edge, forming an even rim that determines how the crust rises in the oven. Each pizza maker senses the dough differently. Hand pressure, rhythm, and stopping point are never exactly the same. A skilled worker needs only 20 to 30 seconds, yet can still create a rim that is even, intact, and stable. These subtle variations in technique leave a distinct personal signature on each crust, enough that two pizzas made from the same batch of dough can feel slightly different from the very first bite. Next, the tomato sauce is spread in precise circular motions. Cheese is evenly distributed across the surface, avoiding the center to prevent the crust from becoming soggy or baking unevenly. Toppings are weighed to exact portions, ensuring that every pizza, whether in New York or Tokyo, delivers the same consistent experience. Finally, the pizza slides into a high-temperature conveyor oven and emerges after 6 to 7 minutes, with a golden crust, fully melted cheese, and gently bubbling toppings. During events like the Super Bowl, when millions of pizzas must be sold within just a few short hours, speed becomes a matter of survival. Pizza makers are not just selling food, they are racing against the clock, where being delayed by just a few seconds can mean hundreds of orders falling behind on the biggest sports night in America. Did you know there's a soda that captured American taste buds 1 year before Coca-Cola was even created? That soda is Dr. Pepper, the result of a successful blend of 23 secret ingredients, originally formulated to mask the bitterness of medicine, transforming it into a fashionable soft drink that has endured for more than a century. The journey of every can begins in 10,000-gallon steel tanks at the historic Waco, Texas facility, the production site closely associated with the brand's iconic museum. To build the foundation for its 23 complex flavor layers, water first passes through a multi-stage filtration and reverse osmosis system, achieving near absolute purity before being combined with corn syrup and phosphoric acid. But the true key lies in the next step. The secret flavor concentrate is added in 2 separate stages to preserve the consistency of the signature formula. After being blended at a 5-to-1 ratio, the syrup mixture is rapidly chilled to 1.7 degrees Celsius, the ideal temperature that prepares the liquid to efficiently trap carbon dioxide molecules during the carbonation stage that follows. Taking advantage of this deep chilled state, the syrup stream is pumped into a saturation unit known as the carbocooler. Here, food-grade CO2 is injected directly into the liquid under high pressure. Because the mixture has already been cooled to a low temperature, the gas dissolves completely and remains stable within the liquid, creating the intense effervescence and signature burst of fizz released the moment the can is opened. To maintain this saturated state, the finished beverage is sent directly into high-speed filling lines. Glass bottle lines can reach speeds of 500 units per minute, while aluminum can lines surge to as many as 1,500 cans per minute. The moment each container is filled, a sealing machine crimps the lid in an instant, locking in the internal carbonation pressure. Finally, robotic arms and automated conveyor systems stack the packaged drinks onto pallets with precise coordination, ready to deliver this legacy flavor to markets around the world. In 2024, Dr. Pepper made headlines by officially surpassing Pepsi to become the second best-selling soft drink brand in the United States, behind only Coca-Cola. However, domestic success does not automatically translate into global dominance. In many international markets, Dr. Pepper does not operate its own independent bottling network and instead relies on competitors such as Coca-Cola or Pepsi for production and distribution. This dependence, combined with its complex flavor profile balanced between cherry notes and herbal undertones, has made Dr. Pepper a peculiar force in the soda industry. Deeply rooted in Texas, dominant among the loyal American consumer base, yet still a selective and niche presence on the global consumption map. Arriving 8 years after Dr. Pepper, Pepsi, originally formulated as a digestive aid, accelerated rapidly into a global empire, generating more than $90 billion in annual revenue. But have you ever taken a sip of Pepsi and wondered, what truly sets it apart from Coca-Cola? And why has this giant remained strong despite entering the cola flavor war as a late challenger? The journey of every can of Pepsi begins with groundwater drawn from the Oligocene geological layer, an ancient source known for its exceptional natural purity. However, to meet the demands of high-speed production lines, the water must still undergo a rigorous technical purification process. First, quartz sand filtration tanks remove all suspended impurities. Immediately afterward, reverse osmosis (RO) technology operating under extremely high pressure forces the water through ultrafine membranes, measuring just 0.0001 microns, smaller than a bacterial cell. This stage completely eliminates minerals and microorganisms, transforming the water into a chemically neutral solvent. Returning the water to this state of absolute neutrality is a mandatory standard. It creates the ideal foundation for blending with syrup concentrate, ensuring that every can of Pepsi, anywhere in the world, maintains a nearly identical flavor structure. Once the water base has been fully standardized, it is directed to the storage area housing the most critical ingredient, concentrated syrup. From sealed holding tanks, the syrup concentrate is pumped into the blending section and transferred into large-capacity stainless steel vessels. Here, automated dosing systems combine the concentrate with purified water and sweeteners according to pre-programmed ratios. Mechanical agitators and flow sensors ensure the mixture reaches complete uniformity before moving on to the next stage. To create its signature sweetness, the facility uses liquid sweeteners. In the United States, typically high fructose corn syrup, while many international markets rely on cane sugar syrup. In a standard 330 milliliter can of Pepsi, the sugar content generally ranges between 35 and 39 grams, equivalent to roughly 9 to 10 teaspoons. In terms of acidity structure, Pepsi primarily uses phosphoric acid, similar to many other cola beverages. However, the calibrated balance between sugar, acid, and flavoring components produces a rounder sweetness, smoother finish, and less dry aftertaste compared to competitors within the same segment. However, sweetness is only half of the story. The other half lies in the burst of refreshment released the moment the can is opened, a sensation determined by the cooling and CO2 saturation process. After physicochemical standardization, the mixture is sent into a carbo-cooler system, where it is rapidly chilled to 1 to 2 degrees Celsius. At this stage, food-grade CO2 is injected under high pressure, forcing the gas to bind tightly within the liquid structure before moving on to the filling stage. Pepsi typically maintains a carbonation level of 3.5 to 4.0 volumes. This means that each liter of liquid contains nearly 4 times its own volume of dissolved gas under standard conditions. This parameter is precisely calibrated to generate fine, sharp bubbles that deliver the signature tingling sensation on the tongue and maintain a lively effervescence even when poured over ice.